Hey everyone, welcome back, and today we're going to be doing something a little bit different again from our usual style of videos. It's going to be the 6th video of my calculus playlist. Now I know it's been well over 3 months, in fact I believe almost 4 months since I made my last calculus video, and I believe that was in our intro to integration, antiderivatives, and even area under the curve for intervals. And so we did briefly, or not briefly, but we did go over the fundamental theorem of calculus, or otherwise known as FTC. But I kind of wanted to kind of refresh our memory on what the fundamental theorem of calculus really is, how and why we use it before we actually kind of move on to our next topic and main topic, if you will, of today's video, which is going to be U-substitution. But more on that in a few minutes. Let's go ahead and kind of review what the fundamental theorem of calculus really is. Now, I'm just going to quickly write out the kind of formulaic definition of what it is. It states that for any integral that we're integrating within a point or under the area of the curve between points A and B of any function, we'll just say f of x, with respect to x, so we'll tag on a dx there. That's going to be equal to antiderivative, or capital F, or sorry, it should be parentheses, I don't know why I added that there, f of b minus big F of A. And what these big F and big F of B and big F of A really mean is big F of x is basically just the antiderivative of f of x. So we're saying that we can always evaluate a definite integral by first finding the antiderivative f of x and then computing its values at the upper and lower limits and subtracting them correspondingly. So we're going to take the antiderivative of this definite integral f of x and plug in the b and a values respectively into that antiderivative and get the difference of those two output values. So let's go ahead and see a very simple example real quick, kind of just to refresh your memories, although we did go about this in my last video, intro to integration in my calculus. So basically, let's say we're integrating from 1 to 5. And let's say we're trying to find the integral of 1 to 5, or the area under the curve between the x-coordinates 1 and 5 of the function 2x with respect to x. I'll just add on a dx there. Okay, so let's first get the first step of actually finding out what the antiderivative of 2x really is. In this case, 2x is our f of x function. So the antiderivative of 2x using the reverse power rule is we'll add 1 to this guy, or we'll bring it back down here. So basically that's kind of like the reverse power rule, the anti-power rule, if you will. And so this is equal to 2x. That's kind of like our big f of x function, right? That's going to be, sorry, not 2x, but rather x squared. Right? And the reason why we got this is because f of x is our standard 2x, and to get the antiderivative, or the integral of 2x, we'd apply our inverse power rule, basically bringing this 2 back up here and multiplying it with this invisible 1 to get us results of x squared. That is our definite integral of 2x. And so this simplifies to really just being the integral, or rather not the integral of 2x dx from 1 to 5 can be simplified to just nothing but x squared. And so this is going to be equal to x squared, and our kind of boundaries are going to be 1 and 5. And so now we've already got the first part out of the way. We've already found the integral of 2x. That's nothing but x squared. And now we want to plug in our two endpoints 1 and 5, or two a and b values 1 and 5, where a is equal to 1 and b is equal to 5 in this case, into our antiderivative. In this case, again, our antiderivative is x squared. And so we're going to plug in 5 for x squared. We're going to subtract that from x squared of 1. That's our a value. Now, if we plug in x or 5 for x squared, we see that that's 5 squared, or 25. And if we plug in 1 for x squared, we see that that's 1 squared, or 1, to give us a value of 25 minus 1, which is 24. And that's it. What does this 24 really mean? Technically, I should put units squared. All this means is that the value of the definite integral of the integral of 2x of the area under the curve between 1 and 5 with respect to x is 24 units squared. So if I were to graph this, and we see 2x, I believe, looks something similar to like this on the Cartesian plane. So let's say x equals 1 is like right here, and x equals 5 is like right here. The area of this under the curve, that's going to be equal to 24 units squared. And we got that by finding the antiderivative, or the integral, of our function 2x and plugging in our a and b endpoints of the area under the curve, 1 and 5, into that integral and finding the difference. And that's really just the fundamental theorem of calculus for you guys. Now that we've actually covered and kind of reviewed what exactly the FTC really is, now let's move on to the main kind of topic of today's video. And that is going to be, sorry, give me a minute, U-substitution. U-substitution. Now, not just U-substitution, because I'm very much assuming that you guys have learned U-substitution before. That's kind of like a prerequisite for today's video. We're going to be learning U-substitution in context of integrals. How can we apply the U-substitution method to integrals? That's exactly what we're going to be learning. Now, for any of you who need a refresher or haven't really used U-substitution too much before, let me kind of explain and give you a very thorough or brief example of what U-substitution would look like. Assume we have the function or polynomial x squared minus 7x plus 12. If you wanted to just factor this, very simply, we see that this is x minus 4 and x minus 3. They're the same thing. It's just this is in factored form. But what if we had something like x to the 4th minus 7x to the squared plus 12? This isn't super easy to just get to know immediately if you don't really know the rules behind it. And so you have to kind of think, okay, we still have the same constants, negative 7 and 12, and we still have the same pattern where our degree, x to the 4th, is 2 times greater than the kind of exponent in the second term. Right? There's just some same pattern, same constants, same signs. It's just that every exponent from our original equation is being multiplied by a factor of 2. And so here we can use something called U-substitution. We can let a helper variable, u, equal this smallest exponent term, x squared. And so if we plug in u for x squared in this original expression or polynomial, we see that we get x squared squared to be x to the 4th, which is nothing but u squared, because u is equal to x squared, minus 7u plus 12. This equation here and this equation here are the same thing. We know that they're the same thing because we let u equal x squared, and so they're the same thing if we apply or plug in or substitute u in for x squared, hence the name U-substitution. All right? Now, have we noticed something yet? This original initial expression or polynomial is the exact same thing as this guy that we substituted u in for x squared for. It's just that instead of having x, we have u. And so very simply, we know that this is u minus 4u minus 3. And so technically, that's it. But wait a second. We were originally given the problem in terms of x. We were trying to factor x to the 4th minus 7x squared plus 12. And so if we give an answer as u minus 4, u minus 3, the grader or anyone reading this answer is going to be very confused. It's like, okay, I don't see u in the problem anywhere. I don't see u in the input. What in the world is u? And so we have to actually take our answer in terms of u and plug back in x squared for it to get it back in terms of x. And so this is equal to, instead of u minus 4, x squared minus 4. Why? Because u is nothing but x squared. And so we just plug in x squared back for all u's and have a resulting answer. So again, instead of u minus 3 as one of our factors, now we have x squared minus 3. And in fact, we can factor this a little bit further. This is nothing but x plus 2x minus 2, using our difference of squares theorem, times x squared minus 3. And now we're really done. The answer to this problem in factored form is going to be x plus 2x minus 2, x squared minus 3. Notice how, without actually using the u equals x squared helper variable, it gets a little confusing to kind of see how that really works, right? Notice how, again, x squared minus 4, x squared minus 3 is quite similar to this answer. But if you had a more complex factor or a more complex equation or polynomial, you can probably see that it would get quite difficult to tell that pattern, and U-substitution would be very key to kind of simplifying and rewriting it in simpler terms to get it in a very simple answer, and just plugging back in x into our final answer that is originally in terms of u. So, now that we've seen what U-substitution can really do in rather simple examples, let's go ahead and see how it's applicable in integration. So, let me just first give you a very crazy integral, right? Let's say we're trying to find or integrate the function 6x times, 1 plus 3x squared. That's good. To the 8th power dx, or in other words, with respect to x. Now, unless you're some insane genius who can just do like a million computations in your head in a second, just off the top, looking at this problem, you won't be able to say what the answer is. It's not possible, it's not logical, it's a very complex equation, at least relatively, and it's not very easy to solve, right? Now, this is where we have to really use U-substitution to rewrite this in a very simpler form where we can actually compute it and just plug in back x for that u's to get a final resulting answer in a more simpler process, right? Again, on a high level, what do we know the U-substitution algorithm or method really is? Again, it's basically simplifying this integration or large function by making that U-substitution that turns this insanely complicated function into a rather simple function. Right, we're just simply changing this huge function into a more manageable one and kind of reversing the chain rule in differentiation. Right? We know what the chain rule is in differentiation. It's kind of like the reverse of that in integration using this U-substitution method. Right? Again, at first glance, this looks like a very complicated function. This looks like an insane function that no one would be able to solve. 6x, you have 1 plus 3x squared, you have all these chain functions here, you have a dx here. You'll probably be very confused when you initially see this, but in reality, it's not too bad once you actually use U-substitution. So, the first thing that we have to do is actually choose which function, either 1 plus 3x squared or 6x, that we want to actually substitute u in for, right? So, basically, we want to actually pick a u so that its derivative du would actually appear in the integral. And so, kind of just, again, this is kind of like the guessing part of the U-substitution. We kind of just have to choose either do we want 6x or do we want 1 plus 3x squared to be our u. In this case, I'm going to let 1 plus 3x squared be my u. So I'm going to let u equal 1 plus 3x squared. And so if u is equal to 1 plus 3x squared, our helper variable u that we just defined above, now let's actually differentiate both sides. Right? Again, kind of reiterate why we're actually choosing 1 plus 3x squared. Again, it's inside this power to the 8th power here, and so it is actually a good choice for substitution. It's like its own separate method, parabolic method, if you will. Right? Now, if we have u to equal 1 plus 3x squared, now let's actually differentiate both sides. And so if we do that, we see that du, like the derivative with respect to u, is going to be equal to, what's the derivative of 1 plus 3x squared? Well, it's just 6x. But since this is actually done implicitly, with respect to u, we have to tag on a dx next to it. Cool, that's great, right? We differentiated both sides. But what is something very important to understand here? Well, we want to rewrite this huge, nasty, complicated function that is originally inputted in terms of x to being in terms of u, where we can solve it in terms of u and just plug back in terms of x to our final answer. So right now, we can change this 1 plus 3x squared to be a u, but we can't really do anything yet with this 6x, or rather with this dx. We have to try to put dx in terms of du. And looking here, we see that du is equal to 6x dx. And so if we want to plug in terms of du for this dx, why don't we try to isolate dx and solve for dx implicitly? So if we divide both sides by 6x, we see that dx is equal to du over 6x. And more than awesome enough, now we can simply substitute du over 6x for dx in the original polynomial, or rather in the initial integral. And so now let's basically we have to plug in back to our original integral, right? It's very important the step to actually integrate back in terms of dx, or rather in terms of du, because it actually allows us to replace that 6x dx in terms of du. That would make the integral a lot simpler, and it would also make it in terms of u. And so bringing this back down here, we see that this is the integral of 6x. Now instead of 1 plus 3x squared to the 8th power, this is now u to the 8th power, because we know that we let u equal 1 plus 3x squared. And instead of dx, it's now du over 6x, because we know that dx is equal to du over 6x. And now, we love to see these type of fractions. These 6x's cancel. One is in the denominator, one is in the numerator, because think about it, this is 6x over 1. We have this invisible 1 as the denominator over here. So we can cancel out these 6x's, giving us the integral of u to the 8th power du. And all of a sudden, we went from this massive function to this very simple function that we should be able to do in our heads by now. And if you can't, feel free to just go back to my intro to integration video. I think I explained the reverse power rule and whatnot very well there. But we see this is going to be 8 plus 1, add on a 1, and then tag down the result down there to be 1 over 9 times u to the 9th power. That's it. Guess what? That is the integral, or answer to this integral. We are done. The answer to this problem is 1/9 times u to the 9th. But wait a minute. Although that is technically the answer, also it is completely correct according to our work, the reader doesn't know what u is. The reader just looks at our answer and he says, okay, I've never initialized u or declared u to be any variable in my input problem. Where is he getting u from? And so again, now we have to put this answer back in terms of x, but that's the much simpler part. Why? Because we know that u is nothing but 1 plus 3x squared. And so let's put back 1 plus 3x squared in terms of u for our final answer. So instead of 1/9 times u to the 9th, this is going to be 1/9 times 1 plus 3x squared to the 9th. And we're done. That's it. Sorry, that was quite a large 9. Okay. Let me try that again. Yeah, that's good. And we're done. The answer to this insanely complex integral is nothing but 1/9 times 1 plus 3x squared to the 9th, just using U-Substitution, right? It's a very straightforward power rule integral. It's a very straightforward implementation once you get to know it. And that's basically it. Once we initialize u, pick our method or function to let u equal. Once we differentiate both sides and isolate the dx, just plug in back in terms of du. Once we simplify the integral and get it all in terms of u and get the answer, all we have to do is just plug or substitute back in for x to our final answer, and that's it, right? Now, we're still not done. I still forgot a very important part to this answer. We learned back in our intro to integration video, in my 5th video of this calculus playlist, that we're not always gonna have a definite integral. We're sometimes many times gonna have indefinite integrals when we're not given any extra parameters, and that's when we need that plus c. We've got the integral of 6x times 1 plus 3x squared dx, but we're not given another point to substitute or plug in to solve for our plus c value. Right, so this is still an indefinite integral, and so we still have to add in or plus any constant c. But now, once we added that, now we're done, and that is the final answer to this integral. It's going to be 1/9 times 1 plus 3x squared to the 9th power plus any constant c for the answer to this integral. And believe it or not, that is actually going to be it for this solution. Again, what have we learned in today's video? We've kind of recapped and reviewed what the fundamental theorem of calculus is. We've also learned how U-substitution works, kind of initializing why we set du to be 6x dx like we saw here, and why we actually solved for dx to isolate that and plug that back in terms of du to cancel out our 6x terms and get it all in terms of u for a much simpler integral. And also evaluate these definite integrals a lot more easier and kind of rewriting more complex functions into simpler functions. So if you guys enjoyed this solution and learned something new and kind of enjoyed this content, please feel free to consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.